Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Thank you to all of our viewers from around the world for joining us. Please let us know where you're watching from. And welcome to our listeners on the podcast version of SETI Live, which is available on most podcast platforms. In a groundbreaking discovery, astronomers have identified an Earth-sized planet closer and younger than any previously known. And today I have the fortune of being joined by two of the discoverers, Melinda Soares-Furtado, who is a postdoctoral fellow and now a professor in the Department of Astronomy at the University of Wisconsin-Madison, and Benjamin Capistrant, Ben, who is a graduate student at the University of Florida. So welcome in, both of you. Thank you for joining me today. Congratulations. So this is kind of cool. I'm gonna give you an icebreaker here. So, all right, we've got 400 billion planets, 300 million could have parties on the beach, and you've got one itty bitty rock. What's the scoop? What made you say this planet deserves its own headline?
Yeah, I think for me, I was most excited about the fact that we could get, an accurate age because it's part of a moving group of stars. And when you have stars in an ensemble like that, you can actually get accurate and precise ages. And so we knew that this planet was young. It's about 10 times younger than, and we also know that it's transiting a star that's fairly nearby, and that enables lots of follow-up. So it was really exciting to find this terrestrial world that is youthful and is close enough and also transiting to do all of this deeper analysis. It was very exciting, and it had been lurking in the data all along, even though other planets had been previously detected that are much further out than this one.
Incredible. So, all right, let's get back to the science. I will welcome in people after we kind of get this rolling a little bit here. What can you describe some of the processes and challenges involved in making this discovery? What instrumentation did you use? How did you find it? Just kind of give us the story of finding this particular planet.
Yeah, so we used data from the TESS mission. That's the Transiting Exoplanet Survey satellite. And we use the transit method, which involves measuring the brightness of the star. And when a planet along our line of sight passes in front of it, it causes these dips. So from those dips, we can determine the radius ratio between the planet and the star. And yeah, so we modeled these dips using code. So there were part of the challenge for this planet was that there were two planets in the system previously discovered. They were mini Neptune size, a little bit larger. So TESS had only observed this star once, but since then it's been observed 4 more times. So in this new additional data, we were able to pick up this much smaller signal that we were unable to see in the just the one sector of data, just 30 days or so. So with that additional data, that helped us see this much smaller signal, and then confirm it as a planet. Some of the other challenges are just making sure that signal definitely is coming from a planet and not another source like background stars, eclipsing binaries, or other signals like that. So we did that with a combination of ground-based observations and then some statistical codes as well.
The joys of modern astronomy, all programming.
So much of my day is staring at a computer code and not a telescope.
So, Melinda, tell us what makes this sun-like host star and its proximity so significant for the study of terrestrial world evolution.
Yeah, so it's really interesting to find a young planet with this known age that you're able to do these follow-up investigations on, because one thing that we really do want to understand in the exoplanet community is the evolution of a wide range of exoplanetary characteristics, but that includes their ability to retain some of their primordial atmosphere. How does that change as a function of time? And also the active outgassing, these volatile elements that imagine some kind of like volcanic-like activity happening on these planets where there's active outgassing that you can measure. And so early Earth, for instance, is about twice the size that Earth is today. Predominantly because of this primordial hydrogen and helium atmosphere. And so it's interesting to be able to, it's important to be able to trace as a function of time, and of course as a function of the orbital architecture, the separation distance, how these atmospheric changes take place. But if you don't have age constraints, which you often don't, it's really difficult to know, it's difficult to model what is exactly going on. But in this case, we do have this nice age. We know lots about the host star's characteristics. And there's the possibility of doing follow-up investigations to try to understand whether or not there's any signs of outgassing, and basically be able to describe and characterize the atmosphere or lack thereof.
So tell us a little bit more about the actual planet. So this is D. So obviously there's a couple other planets involved with this star. It's got a sun-like star. You've got an age. So what's the age that we're talking about? How does this planet work? Where are we going? What's the story with the actual world itself?
Yeah.
Either one of us, Ben.
Yeah, I mean, so it's Earth-like in that it is about 0.9 Earth radii, so fairly close in size, but very not Earth-like in how close it is to its host star. So its distance is like 5% that of the distance of Earth to the sun, and it is whipping around so fast every 4.2 days. So it's got to be really hot, and yeah, that way it is not like Earth. And while there might be no atmosphere, there could be other processes going on as it's losing that because it's such a young planet still.
Because of that proximity, we think it's actually likely to be tidally locked. And so we're really interested, if there wasn't an atmosphere and it was tidally locked, you'd expect to have this extremely hot and extremely cool sort of differential. But if there is a substantial atmosphere, then you would expect there to be some transport of that heat. And so you'll have a more just a more sort of well-distributed heat temperature that you could measure. And so it'll be interesting to see that. But the dayside temperature, if there is no atmosphere at all, is like 1500 Kelvin. So we're talking about, sort of a magma-like hemisphere at least. And it'll be interesting to learn more about that. But that's what we predict based upon the limited information we know so far, and the likelihood that it likely does not have a substantial atmosphere. But.
So we're not looking at a place that we're probably going to be having intergalactic beach parties on. Okay.
No.
Let me welcome in some folks, and then we'll talk some more about this planet. So let's see. Welcome in from Sweden, Massachusetts, Michigan, Louisiana, the UK, Australia, Texas. I think I already got that one. Where else have we got? California, by way of Tennessee. I think that's it. I know someone else. I know one of my friends is watching and is from Georgia. So welcome in, everybody. Once again, we are talking about this little world, HD 63433D. So
rolls off the tongue.
Rolls off the tongue. I love these license plate names. And so this is a small world. It's Earth-sized, but it's really close in, really hot, orbiting 4.2 days. So we're not looking for life here, but we are looking at planetary formation and evolution. So let's talk about how the discovery of this planet and its characteristics, how do they fit in with our current understanding of planetary formation and evolution, which of course I will caveat this with, the more we learn about planetary formation and evolution, the less we seem to understand about planetary formation and evolution. So, but where does this planet fit in with what we know so far?
I'll say it's an important, component to add to a very limited set of census demographics already. So it's one of 70 systems that we know to be young. By young, I mean less than about 500 million years old. So there's not a lot of systems that have accurate and precise ages at all, much less those that are young like this. And that number, if anyone is interested in the audience, comes. I'm looking at those that are 500 million years old with errors of about 20% or better. Sometimes you have these massive error bars, right? So I'm, sort of doing some quality selection there. And so it's a really important piece of data to a already sparse set. And it is, the closest one in that set and also the smallest. So it's very, very similar in size to the Earth. And so in trying to understand young terrestrial worlds and how they evolve, it's not so much of like, for me, how does it fit into a pre-existing context where there's lots of data? It's as if we're really filling in that parameter space and hoping to understand more. But what's so beautiful about this object is because it's around this really bright star and it's transiting, it enables us to study it in all of these different ways. So it's very amenable to follow up, to do lots more careful investigations, and to start working, comparing this to theoretical models that can take account for the orbital separation and the stellar evolution and its age, to try to understand the observations that we're seeing as more data comes in.
That kind of brings me to the next sort of bit about this. Speaking of the, follow-up observations, what are you hoping to use? What are you hoping to discover through follow-up observations? Do you have that in the works? Is that already planned and happening, or at least, proposed? Where are we at with that?
Yeah, we are looking at using Hubble and hopefully JWST. Thinking about proposal writing and mainly just we don't know how or if these rocky planets have atmospheres, or for what processes are going on, and over the timescales, what timescales they lose those if they do have them. So I think looking for that evidence of the outgassing, like Melinda was talking about, is primarily what we're trying to find.
And Ben, you just submitted the Hubble Space Telescope proposal, so we have one in so far. The JWST call is coming up in the fall, and so doing a bit of work to think about that. And there has been Hubble follow-up of the 2 semi-Neptunes, one of which there was no signs of outgassing, and another there were some signatures. So, or at least some atmospheric loss, I should say. I don't necessarily know if it's coming from outgassing or if it's just photoevaporation. But yeah, it'll be interesting to see this smaller, even closer orbiting world, what's happening there.
So the other 2 planets they're Neptune sized and they're further out, obviously making them easier to discover because they're bigger, so they block more light. What are these a possibility for helping us sort of understand that gap that we have between sort of that like super Earth and sub Neptune sized planet? Do we think that this might help answer some questions if we do sort of get a grasp on maybe the outgassing and the size differentials? Is that a possibility here with this particular world?
It's definitely not a possibility for the terrestrial one, and I haven't thought too much about the B and C, which are at 7-day and 20-day orbits. They're about 2 and 2.5 Earth radii. Yeah, but that's an interesting question of how much of that super Earthness has to do with the ability to retain some of this primordial hydrogen helium atmosphere.
Okay. It's just one of those things that I'm completely fascinated with. So I'm always really interested in figuring out like how this happened, because it's that if you ever see like the old Kepler diagrams with what we call the M&M colors of sizes of planets, and it was like here's a spike and here's a spike and nothing shall be in the middle, and it's still very strange to me.
I would think, though, I mean, just at the risk of thinking on my feet, I would think, though, it'd be very fascinating to search more young systems like this and see whether or not there are, I would expect a larger occurrence rate of these super Earths if it is the situation that, given enough time, they're photo evaporating, losing their atmospheres. I would expect these younger systems, so you'll need ages for them, that's hard to get, to just have a higher occurrence rates, a higher instance, because they just haven't had enough time to really lose that material and make up, this. I think you're talking about the Radius Valley, right?
Yeah. All right. I think we've got a couple more to welcome in. I saw, Frankfurt. So from Germany, welcome in, more Massachusetts and more UK. All right. And Alabama. Okay. If you have questions for Melinda and Ben, please feel free to put them in the comments. I'm keeping an eye on them. My co-producer is keeping an eye on them. So we're going to try to get through some of these. I've got a couple, and I definitely want to ask one of these, because I'm curious here. So Nikki is asking, what name would you give to this planet if you could? And you can both answer this one, because maybe you have different ideas of what you would call it.
I've thought about it, if you haven't.
Have you? Ben,
Yeah.
please. I've not thought
I don't know
about
if
it.
I'm
My
allowed
parents always
to.
want me to name it after me, which you're not allowed to do. I'm like, first off, no one needs to be naming things after themselves. Okay, number one, Mom. But anyway.
I don't know if probably not, because of copyright, but there's a lava planet in Star Wars, and ever since we decided that it's a lava planet, that was the name I would like to go with. But
you want to name it Mustafa? Got it. I will show my geekiness. You can't see that I am surrounded by Star Wars stuff. Don't worry. I understand.
Yeah.
I know a lot of scientists, when they make these discoveries, that it's always sort of a question of, do I get to name it? How do I name it? What can I name it? And I know a lot of it is very tightly regulated by the IAU. I used to work on meteor showers, and when I found one, my friends were all, "Do you get to name it?" I'm like, "Well, yes and no. It's basically like there's a naming system I have to follow. It's not very exciting." So I keep hoping that we can start naming some of these exoplanets, because there's, what are we up to? Almost 6,000 now. So, you answered that question. So we are saying that this is pretty much a world covered in lava. It is that hot, correct?
At least a hemisphere covered
At
in
least
lava. That's not as good of a headline, though. Lava hemisphere, than lava world, right? But yeah.
So,
I also just want to point out that this is a moving group that was the topic of Nancy Grace Roman's thesis, the Earth's major moving group. And so, naming it Roman might be very cool as well. Although we have a upcoming mission also called this.
We could just call it Grace. I think
that's nice.
Yeah. So we have a tidally locked, hot, young planet orbiting close in. What for you was the most exciting part about this discovery? Either of you.
I love the fact that it's in this co-moving group, and it was a lot of fun to try to figure out in a huge volume, limited sample of stars, who belongs to this co-moving group, looking at three-dimensional kinematics and the rotational sequences. There's a very mass-dependent rotation sequence that clusters have. We're actually doing much more work on this now. We're expanding that volume, and there was a lot of missing information in the kinematics. Some of these stars needed basically z direction, the radial velocity information. So we're actually taking that data right now. What's amazing is the Earth is immersed in this moving group. So there's both northern hemisphere and southern hemisphere targets. So it means we can use telescopes in South Africa, in Tucson. And because it's so nearby, this star in particular is like 20 parsecs away, even the white dwarfs in this system, in some cases, are bright enough to be observed. So we can look at the ages that are determined by that white dwarf sequence, by the more massive stars, and we can search for more planets. So I really loved digging into this larger population with the recognition that there could be many more terrestrial or other size, but I'm interested in the terrestrial ones, terrestrial size worlds orbiting these young stars, and that are all, not very far away and bright. And even though people have been looking with previous test data, recognizing that as we get more sectors of data and we build up that underlying signal within the noise, these shallow transits, begin to become discernible. So I'm really excited with every new year of test data to explore this nearby stellar neighborhood of young stars, and to look at the distribution and the sizes of their planets. So I got really excited about sort of the population that this planet is part of.
That's really neat. I like this idea that, being able to sort of determine that it's part of a population of stars with known ages, so that you really can get a feel for this. That does seem to be one of the bigger questions we have in astrophysics is, well, how old is the planet? How long does it actually take planets to form? I mean, we're still figuring out how long it takes galaxies to form at this point, and the information coming back from JWST is game changing. We're heading towards the end of our hour, or half hour. I really want to ask both of you. This has been kind of a major discovery. We've been trying to talk to you guys for a while about it. It made lots of headlines, and I feel kind of bad that has kind of quieted down a little bit, because it is a really interesting discovery. How has it impacted your career, and how does it impact the search for habitable worlds? Will this affect that search as well?
Great question. I think it's really emboldened the ability to write many more proposals, not only for follow-up for this planet, but with the goal of searching for more planets in Ursa Major, and really pointing out, how valuable it is when you find them, how, the diverse ranges of sizes that we're going to be expecting here, but also, that they're amenable to this follow-up. So it's emboldened that search. And so I now have a new graduate student whose entire focus is going to be Ursa Major for the next several years, and is learning to do everything from taking the data to analyzing it, to building pipelines, to searching for the planets. It's also made me very excited for searching for planets in other ways. So in addition to the transit method, what can we do with these young stars in terms of looking for planets with the radial velocity method? So I think being able to point to the fact that there's this publication and this major discovery, not just one planet, but now 3, it is really going to embolden the ability to continue that work, and to ask for support to do that.
And Ben, how about for you? How has this discovery, this paper, changed the trajectory of your career, or anything else?
Yeah, I mean, this was my first planet detection. I mean, like my second paper, I've always been interested in planets, and I've been trying to get into the field, and I just started grad school, so it was just such a cool project, and I was just so happy to be a part of it. And after looking at code and classes, and mainly looking at stars and stuff, I just get really excited by planets. So it was a really cool project and whole, and I want to keep doing them. Want to keep finding more planets.
So Ben, this was an undergraduate research project for you?
Yeah, I was a post back, so it was in between undergrad and grad school.
That's incredible. So I just want to encourage people who are watching that, if you're an undergrad, it is vital to do research, and the opportunities are there. You sometimes you don't even have to seek them out. The professors will come to you, but if you are interested, go ask a professor. They will have work for you. Melinda,
Ben's being a little humble. This is his second paper. He did one. He did one before this with me. He's outstanding. I really love working with undergrads like Ben, like in general, but it has been so fun with him. And it's been an incredible experience. But yeah, this is his second paper.
Yes, sorry.
That's
That
new.
was a fun project too. Yeah.
Yeah,
Out
was
of
on young
curiosity,
stars as
what
well.
was the first one?
Yeah, young variable stars. So also using tests, but looking at a sample of stars.
Produced the largest catalog of stars being occulted by their own circumstellar debris, and characterized what those signatures look like, also using test data. Yeah, so
That
the
sounds
young
cool.
star theme is going strong with you. It was a huge catalog. I think it doubled the known sample of that particular type of stars. That's,
All right, I think
he's modest.
what I'm hearing here is Ben needs to learn to blow his own horn a little bit over there. So congrats, Ben. You are clearly doing more than you're letting on, and so
Thank you.
Congratulations.
Thank you.
Ben, people want to know, and I'm willing to put this up here. What are the pictures behind you?
Oh, these ones or
Yes.
these.
Oh, the patches.
These are
No,
just
what are the patches behind you? Yeah, what are the patches
oh,
behind you?
they're just some space stickers. Got like a big package of space stickers on online, and all my friends, yeah, that's what they know about what I do is, so yeah.
I understand. I have a stash. My friend just keeps sorting them into smaller and smaller or bigger and bigger piles depending on what they are. But yeah, if you go to basically any conference, stickers are like the favorite giveaway.
Mm-hmm.
Oh, right. I love how people are teasing me about the title of this, but that's okay. I felt good about it. So Melinda, what's next for you right now?
I'm working on a bunch of projects. The one that I'm most excited about is I'm excited about the upcoming launch of Roman, which is going to happen in October of 2026-ish. That's what the projection is. And I'm excited about looking at young star forming regions like the Orion Nebula to look for free floating planets. These are planets without any star at all. They're bright from their formation, just leftover thermal energy. So you can monitor them in the infrared. And I'm excited at trying to understand, were they ejected from stars or were they born? Much like stars are formed from cloud collapse, you'd expect differences in their motions compared to the other distributions if they were ejected. And I'm also excited about looking for transits around these free floating planets, essentially a way to look at moons that are orbiting free floating planets in space, and to basically try to detect moons outside of our solar system for which further follow-up and confirmation and characterization would be possible. So yeah, really excited about exomoons with Roman, and lots of work on that front is happening. We have two papers. If you look up my name and the TEMPO, TEMPO, which stands for Transiting Exosatellites, Moons and Planets in Orion. We've been working on simulated data and expected yields, but we think it would be an awesome thing to do. And we're trying to convince more folks to get excited about it so we can get adequate time.
I would love that. We need the exomoon detections now. Like that's next. Come on.
We have some really awesome candidates out there. They're large, but it's hard to get confirmation. And yeah, I think free floating planets have a lot of potential in that arena.
So we haven't discovered any yet. Is that correct? Like that hasn't happened yet.
None that are confirmed. There's some through transit timing variations. David Kipping has been working on this front for a long time, among others, and there's some really awesome candidates, but no confirmation. But moons are really plentiful in our solar system. Over 200. In fact, like 3 more were just discovered, I think, in February around Uranus and Neptune. So the idea that these could also be potential worlds that we should be looking into, and that we can learn more about them through follow-up is really exciting to me.
Well, good luck with that. And I would definitely be keeping my eye open for any stories on exomoons, because I think that's going to be like the next wave. And I'm very excited that I now know someone working on it. Ben, how about you? How has all of this changed? You're now a graduate student. You're at University of Florida. So obviously it's kind of had a big impact. Partially, right? I'm sure this was already in the works, but has anything else happened for you?
Definitely. I mean, yeah, these guys got me into grad school, and it's just all the research experiences. I'm just so grateful for it. I'm now looking at stellar flares on planet hosting stars. Still using test data for now. But yeah, looking at M dwarfs specifically, which are really good targets for finding planets around, but they're also very active. So it's kind of a trade-off, and I'm looking for those signatures to see how we can inform our studies of planet atmospheres and other ones like that.
Fantastic. Well, good luck on that as well. I think all very important research, all very exciting, and I definitely want to have you guys back when you next have something to talk to me about. So, keep me in mind when those press releases come out. And thank you so much for taking the time to reschedule and to join me here today. So much appreciated to both of you.
Thank you for hosting this, and this has been a lot of fun.
Yeah, thank you.
Great. Thank you, everybody, for watching. Just to remind you, the SETI Institute is a 501c3 nonprofit. Your bits, your Facebook stars, your super chats all go to our outreach program. So thank you so much for being here and for supporting us. If you want to make a monetary donation, you can go to SETI.org/donate now or give now, but you can just go to SETI.org and there's a big red donate button. And, join us next week. I don't have it scheduled yet, so I don't know what to tell you it's going to be. So it'll be a surprise for everybody. So we'll see you all here hopefully next week back at SETI Live. Thank you, everyone, for watching. All of our viewers on Facebook, LinkedIn, YouTube, Twitter, and Twitch. Much appreciated that you all joined us. And again, thank you to our guests, Ben and Melinda, for joining me today.